Hello wonderful people, welcome to my video. Today our topic of discussion is gamma function, as you already know since you clicked on this video I guess. So let's begin. Welcome back and let's begin. So let's take gamma function. So let me give the heading gamma function. And I will begin with how you write gamma in the notation. So it's a capital letter of gamma. You can consider it as half a t. That would be simpler. And if we say the argument is n, people write it like gamma of n, or maybe they just put like this and inside they write n. Or maybe if the argument is n plus 1 by 2, they write it like this, gamma of n plus 1 by 2. All of this is essentially the same thing. It is just different people writing it different ways. So we can write gamma 1 by 2 like this. Yes, gamma of pi as well. I will say where the limit is, what you can write inside, what you cannot. But let's start. So let's define what gamma is. So gamma of n is defined as, gamma as a function of n is defined as an improper integral from 0 to infinity of e to the power minus x, x to the power n minus 1 dx. It's an integration over the variable x, maybe any variable, doesn't matter. What matters is n and n minus 1 and the terms. Okay, so it's a integration or improper integration. So let's try to find some useful meaning out of this integration. So let me consider this as I. If I is 0 to infinity e to the power minus x, x to the power n minus 1 dx. So this is a product of two functions inside an integration of the variable x. So we can use integration by parts. So if we use integration by parts, I am considering this as the first function and this one as the second function. So if I consider this one as first function, x to the power n minus 1 will be written as it is, and we will integrate this part e to the power minus x, which will give us minus e to the power minus x. Integration of this part. Since this part of the integration is complete, we can apply the limits now and carry on with our further integration. 0 to infinity, differentiation of the first function. So it will be n minus 1 x to the power n minus 2. Yes, and if we integrate this one, so we will get this. So the same, we can write minus minus plus and e to the power minus x dx. Okay, so let's try to find out what this has the value of. So what's the value of this one? So it can be written as x to the power n minus 1, minus sign over here, and this minus can be utilized to reciprocate this, and this will be the same function if we apply the upper limit. So limit would be x tending to infinity, and the second part would be minus 0 to the power n minus 1 divided by e to the power 0. This completes the first term, and the second term, since n is independent of x, we can say that n minus 1 can be written outside the integration. So let's put this as e to the power minus x, x to the power n minus 2 dx. You might have got where it is going, but let's try to find out the value of this one first. So when we put the limit infinity to infinity, it will reduce to the form infinity by infinity. So in this case, as you may know, we will have to apply L'Hospital's rule. So if we continuously differentiate this function x to the power n minus 1, let's say I am doing it in rough over here, let's say x to the power n minus 1, second integration would be differentiation would be x to the power n minus 2, again n minus 1, n minus 2, x to the power n minus 3, and so on. It will continue. So at last we will get n minus 1, n minus 2, dot 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 dot. At the end we will get x to the power 1 or x to the power 0, or maybe x to the power 1 by 2. It will reduce to a finite number. At the end it will reduce to a finite number. That's what I am trying to say. So if you continuously differentiate, it will at the end become finite. But if we differentiate successively to e to the power x, it will never going to change. So it will remain infinity. So a finite number divided by infinity is 0. So it will give us 0 minus 0, since there is 0. So this solves our first term, plus n minus 1. And as I already said, you might have known this. If we put it in the definition of gamma, we can write it as gamma of n minus 1. Yes, we can. Yes, we can. So a very important result, gamma of n is equal to n minus 1 gamma of n minus 1. A very important result to remember. This is the result that will help us to solve many of the questions. So let's just border it. You might take a screenshot since I am going to move to the second page. Okay, this first thing, this you should remember, second thing, this you should remember, and the rest I will discuss. Now if we consider n to be, if we consider n to be natural number, then gamma of n is equal to n minus 1 gamma of n minus 1. We can further say that if we can further write same thing for this gamma, n minus 2 gamma of n minus 2 equal to n minus 1 n minus 2. If we do this successively, you can see that we will at some point will reach 1 gamma 1, since n is a natural number. If n would be a fraction, then 1 by 2 minus 1 would give us minus 1 by 2, and in such a situation we will not reach gamma 1. So it is essential that at the end it is a natural number. That's why at the end we will always reach 1. Okay, so we can write this term apart from the gamma 1 as n minus 1 factorial. And let's write this gamma 1. Let's calculate gamma 1. From if we put n equal to 1 in the definition of gamma, we can write it as n minus 1 factorial 0 to infinity minus of e to the power minus x to the power 1 minus 1, that is 0 dx. So it will become n minus 1 factorial times minus e to the power minus x 0 to infinity, and then we can write n minus 1 factorial times of minus 1 by e to the power x limit x tends to infinity minus 1 by e to the power 0. This term will give us 0 and this term will give us 1, so it is equal to n minus 1 factorial. So the third important result that you must remember is gamma of n is equal to n minus 1 factorial if n is a natural number. Okay, you may take a screenshot. I will move to the next page. Okay, let's do it. Now let's see about fractions. So there can be many type of fractions: gamma 3 by 4, gamma of 1 by 2, gamma of 5 divided by 1, 2, 3. There can be many kind of fractions, but what logically we can calculate by hand are in which the denominator is of when denominator is equal to 2, like 3 by 2, 1 by 2, 5 by 2. In the reduced form, like 8 by 16 can be written as 1 by 2. So they are the same thing. In the reduced form I am talking that denominator must be 2, so we can calculate them by hand, but the rest of them are so rigorous to calculate because we'll have to use integration, and it cannot be done using hand many times because the number may be an irrational number, so we can't even get the actual value. So we use computers for those kind of numbers, but for the base 2 or the denominator 2 kind of fractions we can actually calculate. For that we will use two things, that is gamma of 1 by 2 and that the relation that we just derived, that is gamma of n is n minus 1 times of gamma n minus 1. This relation and the value of this one, that is, I am just giving you a little bit of information, that is equal to pi. We will calculate this right now, but I am saying just to be clear about what I am talking about. For example, if we want to calculate 3 by 2 gamma, we can write 3 by 2 as gamma 3 by 2 as 1 by 2 gamma 1 by 2, which will give us root pi by 2. Or if we want to calculate gamma of 5 by 2, we can write it as 3 by 2 gamma 3 by 2, and repeat the same process for that in this one, that is 1 by 2 gamma 1 by 2. But we know that this value has root pi by 2, so we can directly write it as 3 root pi by 4. So we can use just gamma 1 by 2 to get rest of the denominator 2 values, since we can subtract minus 1 from that and it will remain base 2. Okay, so let's find the value of gamma half. Let's prove that it is equal to root pi. So let's try to find out the value of gamma half now. Let's begin. So it's a rigorous proof, so it may take some understanding of coordinate systems as well. If you want to prove it simply, you can use the Cartesian system for proving it, but it will take a lot more effort. So um, if you don't know about the polar coordinate system, I would suggest you try it by Cartesian system by your own if you want to solve it, or you can just remember the value of half is root pi, and here is the proof for polar coordinate system if you want. So let's start with gamma 1 by 2. So by definition we can write v 0 to infinity e to the power minus x, or let's say this time t, because we will substitute x later, which will be helpful. I will tell you later. E to the power minus t, t to the power 1 by 2 minus 1 will be minus 1 by 2, and dt. Let's substitute x square in place of t. Let's see what we get. If we substitute x square in place of t, let t is equal to x square, then we can write dt is 2x dx. Let's put the values in that. So let's say it is gamma 1 by 2 is equal to 0 to infinity e to the power minus x square. In place of t we can write x square, and it will cancel, and just it will become x to the power minus 1, and for dt we will write 2x dx. So we can see this x and this x will get cancelled, minus 1 plus 1 0. So we can write it as gamma 1 by 2 is equal to 0 to infinity e to the power minus x square. This 2 will can write outside, and x cancelled, dx. Simple. Now we can again write, this will imply this, and that we want to imply that. So gamma half can also be written as 0 to infinity e to the power minus y square dy. Why are we taking dx and dy separately? We are trying to do a surface integral this time. So the result would be very simply obtained if we do it by surface integral. So for surface integral, we'll just multiply these two equations, and we will get gamma 1 by 2 squared multiplied in left hand side. 2 times 2 is 4. We can write 0 to infinity, x equal to y equal to 0 to infinity e to the power minus x square times e to the power minus y square can be written as e to the power x square. Rather, I should show the steps: dx dy, and it can be written as 4 times 0 to infinity e to the power minus x square plus y square dx dy. Yes. So if we convert this whole to polar coordinate system, we can say x square plus y square is equal to r square. Okay, and if we try to take, say, this is d theta and this is r, and this r could be r d theta, and if we say that dr changes like this whole surface would be r dr d theta multiplied two sides. So we can get this surface, this infinitesimal surface, which we can substitute for dx and dy. Yes. If you don't understand this, I will suggest that you should study about polar coordinate systems and different coordinate systems like spherical, cylindrical. Then it would be much easier So gamma half squared is equal to this much, and we can write it as 4. R would be from 0 to infinity R. We can use any amount of R we want. All the R would be covered, but theta, it must be positive. Theta must be positive. So for theta, for this to be positive, it should be in the range. Sorry, not theta should be positive, but rather the value of it should be positive. So it would be confined to this quadrant only, not the other quadrants. Therefore, the limit of theta would be from 0 to pi by 2. And e to the power minus r square, we substituted this. And for dx dy, we can simply write r dr d theta. And theta is equal to this much. So 4 times of, we can take r terms one way, 0 to infinity, e to the power minus r square r dr, and this term 0 to pi by 2 d theta. It is a simple integration. We will have to use limits in this one, so its value would be simply pi by 2. So 4 times pi by 2 times this infinite improper integral. So e to the power minus r square dr. If we substitute z for r square, if r square is equal to z, then r would be root z. This implies dr is 1 by 2 root z dz. Okay, so we can substitute the values over there. So from 0 to infinity, we can write e to the power minus z. For r, we can write z to the power 1 by 2. And for dz, we can write, sorry, for dr, we can write dz by 2 times z to the power 1 by 2. Z to the power 1 by 2, 1 by 2 cancelled. 2 times 4, they also get cancelled. And for e to the power minus z dz, we get pi times of 1. This is the same integration we did at the end of to calculate gamma of 1. You can refer to that integration, or you can integrate it by yourself. It will give you 1. Okay, so it is pi. This implies gamma of 1 by 2 is nothing but under root pi. And that's it. So I think the session would have been very boring, me writing on the paper, you listening to me. If you made to this far, please consider subscribing. In next video, we will solve questions from the book H.K. Das. I am naming the book because many of you may be asking which are the questions are we going to solve. So the book would be H.K. Das, Mathematical Physics. You can go through it if you want, and in the next video we'll meet and solve them. Thank you very much.